to talk about that no more. I want to just talk about now that we have X of L, X of C, and now that we have R, these are all in ohms. These are all resistances. So I want to find out here what happens in terms of finding a total, well, I'm going to call it, can't say all total resistance or reactance, we're going to say impedance. So we have to find impedance, and also to find current and the voltage across each component. And we know already some about, phase relationship that exists between the resistor, inductor, and capacitor. Kind of briefly to say that on a resistor, voltage and current are in phase. There's a phase shift on a resistor, right? Now, on a capacitor, we have ice. Current leads capacitor, current leads voltage and capacitor. And of course, we have Eli. And that is an inductor that voltage leads current. Okay, so we have these. So if I'm looking at these all three at the same time in a phasor as well. Once we figure all of that, I want to also take a look at the power. How these things are using power. It turns out there's some use power. Some, we don't want to say they use it. We're going to say storage power. Okay, so we don't have to. Now we know if we use power, uses up power, and power goes up in terms of heat or whatnot, that's the wattage. We know that's watts. We're going to learn that we don't have watts. We have watts when it comes to resistor, but not an inductor or capacitor. We don't use watts. So we have to learn what that is. Power as well. So there's a lot that lies basically in this particular problem. So I want to kind of put some formulas out there, and then, as I said, we can put some numbers in there later, and then kind of deal with it. Now, in this case here, I'm going to draw the phasor. I'm going to assume, I'm going to just make that assumption, okay, because if I'm going to write phasor, I have to put some draw it. To draw it, I have to put some numbers in here. So I'm going to say X of L, let's say, is 4K ohms. And let's say X of C is 10K. And I'm going to say that the resistor itself is going to be equal to, let's say, assume is equal to 2K. So we have, so I can draw something. So I'm going to draw the phasor. The resistor, kind of voltage are in phase. So that's the resistor right there. If you remember, X of L was going upward. So here we have X of L is 4. 1, 2, 3, 4. That's X of L leads. E leads I. X of C, however, the current in this case here falls below, and it's going to be 10. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know, guys. But down here is 10. This is X of, that's X of C. So this is X of C, and this was X of L, right? There's put the L. Looks like the L. Okay, so now this is our phasing. You see what's going on there? So now we say, well, okay, I want to find, I know that X of L and X of C are 180 out of phase. So we can actually algebraically add them. I can add these guys together. I can add X of C and X of L. It's just a simple one. But you have to subtract. Subtract because one goes to a negative number, one is positive. So if I want to find a total reactance, I don't care, it's an inductive or a capacitive reactance. whichever dominates. Right now, I'm looking at capacitor is dominating here. So it's gonna fall below, in this case, here, 4 quadrant down here. So I'm gonna subtract the 2. So if I subtract the 2 from here, what's 4 minus 10?
6.
I think it's 6. So 1, 2, 3, 4, 5, 6. I'm gonna draw what's other one right there. I'm gonna call it, let's say, X total. So X total is simply subtracting the 2 x's, and I end up with X total. Now, you can see what's going on here now. I can see that where the impedance is going to be, where it is, that's right there, is the impedance, right? That's our friend Z. And it's got to be negative. You know it's negative because it's more capacitive. If the inductor was dominating, the theta would be positive. So here now we have Z. So if I want to find out if we Z then, Z is going to be equal to square root of R squared plus x of, well, you can say x of L minus x of C squared. And remember now, whatever comes up here, negative, when you square negative, it's going to be positive anyway. So this number here is always positive. Okay, I'm just going to put it down here. When you square it, that will be positive because it's our friend x of t right there. Okay, so that's total impedance. Obviously now I can find out the current. I is equal to V over Z. V sub R is I times R. V sub L is equal to I times X of L. V sub C is going to be I times X of C. So, just for the fun of it, we can put some numbers to these things. Let's see, obviously I don't have the 10, I have the voltage yet. But I just want to see, what is that Z is going to be equal to?
7.2 kilo.
Okay, 7.2 kilo. Okay, that's a very ugly number, okay? I didn't do a good job of that. Anyway, so this would be finding the impedance. Given the voltage, you can plug it in there now and find the rest of it. Now, the same thing is true about when the voltages add up, remember? The voltage also is supposed to add up as well. So total voltage is equal to square root of, in this case, V sub R squared plus voltage across L minus voltage across C squared. So this formula also is true. Because now we have voltages that we are dealing with. So that's also total voltage supposed to add up. They add up like a vectors, like we talked about here. Now, next thing is talk about, at this point here, I want to talk about a power. When I'm looking at the power, we're going to have also a triangle with power. So let's take a look at the power here. Power is going to be equal to, I'm going to draw a little triangle. Down here, the resistive power. And that is, sometimes they call that real power. Real power. Real power meaning that, okay, well, this actually is the real power used. Real power. Now, over here, there's going to be a reactive power. So P sub X is a reactive power. So it will be, right now, it looks like small capacity. So that would be P sub X. That would be, called a reactive power. A reactive power. Now this one was watts. this one is going to be voltage ampere reactance, which is bars. Voltage ampere reactance. Now, this happens to be actually total power, or we're going to call it apparent power, P sub A. And that's apparent power, apparent power. And apparent power is VA. So we have VA, we have watts, and we have var. Because, you know, capacitor and motor can say actually saves power. It's not using it, it's kind of storing it in a sense. So it's not really fair to say that, you know, it uses real power. Real power is the one actually used in this case here. So, you know, in this case, let's say the power company, when they charge you, they charge you on the watts. So also, they want that to be watts going on the reactor. You store it, and you kind of feeding off the power there. You're actually storing the power. So they run something, run a test on you to find out if it's really, it's a real power you're using. And that's anyway, actually they use to figure it out. They're not going to check people, just flags. If something comes up, it's a flag, flags up. So something is happening. Now here's the thing though, that I'm looking at these, and guess what? This guy right here is actually our friend Taylor. Now I didn't talk about Taylor here before, so we didn't find Taylor. Let's go ahead and put that from right here. Theta.
Hey, Professor.
Is going to be equal to yes.
Yeah, I got a question just backing up here.
Yes.
Is I should be V over Z, shouldn't it?
I'm sorry, V over Z. Thank you. Thank you.
No problem.
Yes.
Yes, as
We have to edit that on the camera there. Theta is equal to the arctangent. X of T over R. X of T over R. Makes sense, right? Right. X of T over R. Because X of T could be negative. If it's negative, it means negative angle. X of T over R. This case here is going to be negative. X of L is smaller than X's. And so, anyway, now that I'm looking at this, I'm saying that, let's add a couple more things here. And that is that P A is equal to square root of piece of X squared plus piece of R squared. That also is in there. And another thing is that cosine of theta. Cosine of theta. Cosine is going to be the adjacent over the hypotenuse, right?
Yes.
So that would be PR over PA, huh? This is actually, cosine of theta is actually known as power factor. Power factor. I think I talked about it a little bit on the shell there. And most of you guys came up with a formula. And that formula was this, PR over PA. Real over the apparent. So cosine theta is power else I can add to this that need to be fit in there? I think that's the size of it. This kind of makes sense a little bit.
Yeah.
Yes.
Yeah. Also, reading the chapter last night, and I got a formula for reactive power. I squared times XL.
Yeah, that could be also, yeah, that's a good idea. Very good. We haven't talked about that part of it yet.
Oh, okay, I didn't know.
Good idea. Yes, let's do that. Let's finish up. He says, okay, let's go ahead and find out other formulas, which is pretty good. For power, for real power, is going to be I squared times R. Yes?
Yeah, I squared times R.
And P sub x is going to be equal to I squared times x of t.
X of T.
Yes?
Yeah.
And P apparent is simply is I squared times z.
Pretty much Ohm's law.
Huh?
Pretty much Ohm's law.
Yes, yes.
Isn't theta also inverse tangent px over pr?
Yeah. The px over here. Yes. You also find that, yes. Yes, yes. So that now should sum it up. That should all be all the formulas for power and RLC series circuit. Now you can see what's going on here now. All of this thing can change if the frequency changes, right? I mean, if I change the frequency, watch this. If I get this frequency, whatever it is, to go slower, that means that when I go slower, I mean that the frequency is going to be less. So look at the x of one, x of c. Which one is going to be affected? Well, you're gonna have them both going to be affected, right? Okay, so what happens to the x of L as frequency goes up?
Goes down.
X of L goes up.
Okay.
As the frequency goes down, x of c goes up, right? So as the lower frequency capacitor is dominating, you see that? And higher frequency, the inductor seems like it's going to be dominating, isn't it? Yes or no?
Yes.
So that's what I'm saying, that thing in here is right now at a certain frequency. As frequency changes, this whole phenomena here, in terms of actual value, is going to be completely changed. Because I'm assuming at a certain frequency, these are the resistances. But if I'm here playing with the frequency, all the bets are off. Things are going to be different. And as a matter of fact, in the iLab is what you're going to do. You're going to actually set up the frequency and do everything, and then, so whatever. What's going to change the frequency here? Well, obviously things are going to change. All the voltage is going to be changed, one is going to be dominating the other versus the other one. So it all depends on what's going to happen. But I can tell you in general that the lower frequency is the capacitor dominance. High frequency is series circuit. Talk about series RLC circuit, not very parallel circuit. Series circuit, that's going to be the case. Because remember, higher the resistance, higher the voltage drop. So higher the resistance, higher. Also, there's a voltage going to be across the one which dominates. Less voltage going to be across the one that has the less resistance. Okay, so we learned about that in our doing our lab, so iLab. So that's why I say it's good that we have. Let's go ahead and, without any further ado, let's take a look at the iLabs for week 3. iLab 1. Yes, you had a question there.
Yeah, you said frequency goes up, X of C goes down,
Yes.
and frequency goes up, X of L goes up.
Goes up.
Okay.
You got it.
You got it. Okay. You want to stop the camera for a minute?
No.